Linear programming is particularly useful as a tool when solving application questions. Please take a moment to pause the video, familiarize yourself with this question. All credit for this question and its graphs go to ck12.org. Knowing that we have a total of $10,000 to invest and 3 different places to put it, you would think that we needed 3 variables for this situation, when in fact we do not. Before we begin writing all of the constraints in an effort to maximize our return on our investment, we're going to begin by defining some variables. X is going to be a representation for the amount that we will invest at 5%. Y will be a representation for the amount that we invest at 7%. And instead of using another variable for 10%, because we know we're going to need a third variable for the writing of the objective function, we're going to use a slightly different technique and say that the amount that we invest at 10% is everything that's left over after 5 and 7% have been invested. So this one is actually going to be represented by 10,000 minus X minus Y. Using those 3 representations for the 3 amounts, we can write our objective function. We'll start with Z as a representation for the maximum amount of return that we want to get. And we're going to make 5% off of the X, we're going to make 7% off of the Y, and we're going to make 10% off of that leftover amount, 10,000 minus X minus Y. Now, because of the placement of the X and the Y in 2 different places in the equation, we can clean up this objective function just a little bit, and you can check my algebra, but we're going to take this down to 1,000 minus 5% of X minus 3% of Y. And that's the cleaned up version of the objective function. If you want to leave it in its original form, the green one, you're welcome to, but because we can do some simplifying after some distributing and combine some like terms, we can make it a little bit easier to work with. All right, now it's time to write some of our constraints, and we have a lot of different requirements for this particular situation. Requirement number 1 is we know that all of the amounts of investments need to be non-negative. So we're going to say that X needs to be greater than or equal to 0, Y needs to be greater than or equal to 0, and 10,000 minus X minus Y needs to be greater than or equal to 0. If we want to rewrite this one as a easier to graph linear inequality, we can solve it for Y and say that Y is less than or equal to 10,000 minus X. Now there's 2 other parts of this that we have not handled yet. We have not handled the fact that we do not want to invest any more than $1,000 in the high risk account. That's this part. And we have not handled the part yet that says that we need to invest at least 3 times as much in the municipal bond as in the CD. The municipal bond is X, the CD is Y, and that inequality will look like this. We need this amount to be at least 3 times that amount. Dealing with the no more than 1,000 in the high risk account, we're again going to use our statement for the high risk account amount, 10,000 minus X minus Y, and we know that that can't go over 1,000. And again, we can solve this for Y, making it a little bit easier to graph and a little bit easier to visualize. We end up with Y is greater than or equal to 9,000 minus X. So all cleaned up in all of its different versions, we have 1 constraint, 2 constraints, 3, 4, and 5. 5 different qualifications for amounts of money that we could put into all of these different accounts. Graphically, we're going to place all of these on the same coordinate grid and look for the, in this case, 5-layer shading that will cover for all of these inequalities. And if we were to do that, and again, thanks to ck12.org for the picture, here is the picture representation of that. We have our X is equal to 0 line. We have our Y is equal to 0 line across the middle. We're to the right of X equals 0, and we are above Y equals 0. We are below y equals x over 3, which is just the restatement of this inequality if you wanted a different version of that one. And then we are above 9,000 minus x and below 10,000 minus x, which is this one over here. And here is our region right here. This is where we're going to see our 5-part shading for all of those inequalities. 2 of the corners are very easy to identify. We have one right here, and this is at 10,000, 0, and the one right here, which is at 9,000, 0. These two are a little bit more difficult to find. But if you remember, we are just looking for the intersection point of 2 different lines. So if you do not have a graphing technology available to you, the visualization of this, a graphing technology that would give you those points, the visualization of this allows us to say that this intersection point, I'll put a red star here, that intersection point is at the intersection of x over 3 and 9,000 minus x. And this intersection point is at the intersection of x over 3 and 10,000 minus x. Solving each of those individual equations for x would give us those 2 intersection points. And if you want to pause the video and try to solve them, I think that would be a fantastic idea. If you did solve them, you would get that this intersection was at 7,500, 2,500, and that this intersection here is at 6,750, 2,250. That is 2 points that you never would have guessed by looking at those 2 lines and their locations. And that's assuming that you were able to graph it accurately. That's assuming that the scale wasn't wrong. That's assuming a lot of different things. So in this case, the algebraic solution, looking for the intersection points of those lines, proved to be a little bit better. Down here, it was easy. We could see that they intersected the lines down there. But finding the exact point for those 2 intersection points did require a little bit of algebra. All of that being said, and this region being formed the way that it is, it looks like we have 4 points to test to see where our maximum is going to be, where our maximum return on investment is going to be. Testing those 4 points is a matter of just going back to our objective function. We're going to use the easier version, I shouldn't say easier version, the trimmed down version of the objective function after we did some simplifying. And we're going to substitute those 4 points into that objective function. And this is what it would look like. So here's our 2 that were on the x-axis. They got us returns of $500 and $550. Here's one of our intersections. That got us $550. And then this one is going to prove to be our maximum. So the best investment, given the requirements of each one of those accounts, is that X, the 5% investment, was an amount of $6,750. Y was $2,250. And the last one, which was our 10,000 minus X minus Y, our investment in the riskiest account, comes out to be exactly $1,000. So if you're looking to maximize your return, it appears as though you want to maximize the riskiest investment. Are you in a position to do that at all times? No, that's not good management sometimes. But if you have the opportunity and you can take a risk with some money, it's best to put it in those high risk accounts to make back the most that you can.